Hello, my name is Lior Ella. I'm a research and product team lead, and I want to thank you for joining this talk. Today, I'm going to talk about how you can accelerate the timeline for practical quantum error correction with our highly configurable control platform. And I'm going to follow up on Jonathan Cohen, our CTO's previous talk, by giving two concrete examples to show how the OPX can boost your error correction code experiment performance. Okay, so let's get started. The two experiments I'm going to talk about are adaptive parity tracking for ancilla refresh, and I'm going to talk about it in the context of the Google Quantum AI work on repetition codes. And the second example I'm going to give is adaptive error syndrome measurement, which I'm going to talk about in the context of the Honeywell experiment on real-time fault-tolerant error correction. Okay, so let's start with refreshing of ancillas with active reset and active parity tracking. So here we see a simple example where we have two data qubits and one ancilla qubits, and the ancilla qubit is measuring the Z0, Z1 parity of the data qubits. And what we typically do in this scenario is we perform a reset operation on the ancilla after every measurement. So this is what the QA code for this looks like. So here you can see that we have the Z0, Z1 stabilizer measurement right here. And this is how you perform it in QA. It's very straightforward. Secondly, we have the ancilla measurement and reset. So here what we do is we measure, this operation is for measuring, and we put the value of the measurement of the I in the IQ plane, from the IQ plane into this real-time variable. And here we perform a Y operation or a flip if the condition here is true, which in this case means that we figure out that we're in the excited state. So this is how reset operation, active reset operations look like with QA and the QOP. But actually, we can do something much better than that. What we can do is we can perform adaptive parity tracking. And here we're basically performing this logic on the ancillas. And what if you actually go through this and figure out what this logic is doing, you will see that what it does is it gives us a situation where we measure one on the ancilla only when we know for a fact that the parity changed. Okay? So this gives us what was so-called detection events directly from the ancilla measurements. And here you see the logic for this. It's actually really straightforward. Again, with QA, almost looks like pseudocode. But actually there is a real deep advantage here because of the way this logic is handled, and we'll show in a second. So here we again do the 00, Z1 stabilizer, which we perform using these C phase gates. And here we have the conditional operation. Now, if we look at what is actually this condition is based on, we see that it's a XOR of what we did in the previous round and in the measurement round before that. So what this actually means is that we have all of this time to calculate the condition, to get the result and calculate the condition. And with the OPX, actually this is sufficient to give us zero time gap between this operation and this conditional operation using the same timing, gates timing as in the Google paper. So in this sense, this scheme is optimal because it allows us to do zero feedback latency. And so now the question is, okay, so we have this zero feedback latency. By how much does it actually improve the performance of the code? So here we looked into a bit more deeply. And here you can see from the Google paper, 1 over lambda, which is a measure of how increasing the code redundancy improves the logical error rate. What it turns out is that the measurement and reset are actually a really significant part of the round time. And during this time, the data qubits are idle. And this is a very significant source of error. As you see, this blue part here is a very significant source of the total error contribution. So by reducing the reset time, we expect that we'll be able to significantly improve 1 over lambda. What we've done is we performed simulations using STEAM of this model. Actually, and we used the same gate errors as in the Google experiment. Actually, we got a slightly different result, which of course could be an artifact of the simulation, where in our case, we found that 1 over lambda is 0.99, very, very close to the threshold with a 300 nanosecond reset time. But if we remove the reset time to only the actual single qubit gate time, which we put to be 16 nanoseconds, we improve it 1 over lambda from 0.99 to 0.83. And this is a really significant improvement that we get just by having the qubit spend less time idling during the reset. Actually, we can also check what happens when we reach 10 to the minus 4 gate errors. In this case, the idling error would be a more significant fraction of the error. That's what we expect, and we actually see that this is really the case. Here we improved 1 over lambda from 0.81 to 0.55. Okay, so in conclusion, in this example, we've shown how using really almost pseudocode looking like code, we can get zero feedback latency and really leverage the real-time capabilities of the OPX. Okay, so let's look at the next example. Here we're looking at the Honeywell experiment where they've realized a distance 3 color code in trapped ions. And here you basically see the flowchart. So let's see it in a bit more detail. So here you see the error correction cycle. And the first thing you notice here is that there is branching. So based on the syndrome measurements in this first flag parallel circuit part, we will either move to the second flagged parallel circuit part or to the unflagged circuit part. So we have here, what we need here is real-time branching and decision on which circuits we want to perform. So now one might wonder whether it's actually really necessary to perform a real-time feedback or whether it was possible to do this without real-time feedback. So actually what we'll show is that it's really necessary to perform real-time feedback here. And why is that? These two flagged circuits are actually fault tolerant in the sense that they can detect and in principle correct up to 1 polyerror, which is the maximum that we can do with the distance 3 code. However, this unflagged part is actually not fault tolerant, and as we'll show, this is what requires us to perform, to be adaptive and to perform real-time feedback. And why is that? Well, here we see a scenario where in the fault-tolerant part we have 1 polyerror, and in the non-fault-tolerant part we have 0 polyerrors. And this is okay, we'll succeed to recover because we had 1 error. If, however, we had here 1 error, and here in the non-fault-tolerant part we would also add 1 error, this is also okay because there are 2 errors, and so we don't necessarily expect to be able to recover from this situation. However, let's imagine a scenario where here we have 0 errors in the fault-tolerant part, but in the non-fault-tolerant part we have 1 error. This is actually a really big problem because in the non-fault-tolerant part we can have errors such as hook errors, which we won't be able to recover from. So the conclusion from this is that if in the flagged circuit part, which is fault-tolerant, we had 0 errors, we must not go into the non-fault-tolerant part, which means that we have to branch in real time. So this is why real-time feedback is actually required in this case. So let's look at the QA and QOP implementation of this code and show its performance. So here, first of all, as you can see, this really looks like pseudocode. And if you got a chance to look at this Honeywell paper, which is really great, by the way, you would see that they wrote there the pseudocode for this protocol, and it looks really, really similar. However, this runs in deterministic real-time on the FPGA. Okay, so let's see a bit more in detail. So here we have the first flag stabilizer round, which here we wrote is this macro, which basically encapsulates all of the gates that are performed here for the stabilizer measurements. Here we have the branching. Okay, so here we perform the logic that says whether we want to go into this branch or this branch. And on this version, the latest version that I checked, the latency for this is 430 nanoseconds. And actually, it's important to point out that we're always optimizing our compiler and our hardware, so this time can go down from version to version. And so in 430 nanoseconds, in this case, we decided that there was no change in syndrome, and we're moving to the second flag parallel circuit part. And here again, we're calculating the branch, 430 nanoseconds. Here we detected a change in the syndrome in this particular example that we're showing. So we go into this unflagged circuit part, okay, which is shown right here. And then we also update the syndromes. And lastly, we perform the decoding. In this case, it's a lookup table decoder, so it's very simple to implement it in QA. And here we're writing it as this macro. And so this code performs this entire quantum error correction cycle. Here we have the for loop that allows us to repeat this cycle as many times as we want. Okay, so what we've seen here is really out-of-the-box implementation that with straightforward and really something that looks almost like pseudocode, we can get feedback latency of 430 nanoseconds on this protocol. Okay, so let's summarize and discuss a bit more. So error correction and fault-tolerant schemes are really diverse and are really challenging in terms of their hardware control requirements. And as we know, experimental implementations will always run into new issues, so it really requires us to have comfortable code that we can work with that almost looks like pseudocode. And the QOP is uniquely suited to allow for quick iterations of complex schemes with near optimal performance. Thank you very much. And please tune in to the rest of our talks during the APS March meeting. And also come visit us at our booth 609 and snag some legendary quantum swag. Thank you very much and follow us. Goodbye.